Welcome to Mr. Bixel's tutorials. This is the conservation energy problem number 2. Tarzan, with a mass of 85 kilograms, is swinging on a vine. He steps off a branch that is 30 meters above the ground. At the vine's lowest point, he's 10 meters off the ground. How fast will he be going at his lowest point? Alright, first step, draw a picture. Here's Tarzan, here's him swinging down. I've got his mass written in the problem. And I've also got his initial height and the final height. And that's important to notice that his final height is not 0. So, looks like a conservation of energy problem. We pull up our energy flow diagram, and what will we choose for our system? Well, Tarzan has to be part of the system, as does the Earth. Is air part of the system? That's going to be an important consideration for this problem. I look up here in the word problem, and it doesn't say anything about air. So it doesn't say that air is negligible. It doesn't say that you should take air into consideration. I'm worried that we're going to have to think a little bit more closely about this problem, but let's go ahead and start by attempting to solve it. Well, clearly at the beginning of the problem, he's standing on the branch. Got gravitational potential energy. He's not moving, so we can set translational kinetic energy to 0, and thermal energy we'll just set to 0. Afterwards, now he's down here and he's moving fast, so he's got translational kinetic energy. But we cannot say his gravitational potential energy is 0 because he still has a height of 10 meters. So we're going to have to keep a little gravitational potential energy in here, and I'm assuming that cutting through the air is going to result in some friction. He's going to get a little warmer, the air is going to get a little warmer, so we'll put in thermal for right now. Like a typical conservation of energy problem, energy before equals energy after. This equal sign is something we can put in if we're assuming the law of conservation of energy is true. So, gravitational potential energy before, that's the only type of energy present that's non-zero. Afterwards, we have all three. We use our equation for gravitational potential energy, mgh. Our equation for translational kinetic energy is 1/2 mv squared. Gravitational again, and we don't have an equation for thermal, so we'll just keep writing thermal. We continue by substituting in the numbers for mass. There it is, for gravity and height, and we get 24,940 joules that are present before. 24,940 joules. So afterwards, we know there's 24,940 joules somewhere between all three of these. We substitute in the numbers for mass and velocity here. We don't know the velocity, so we just bring the variable v after down. Here's gravity after, and we bring thermal down. In this step right here, we run into a problem. We've boiled our equations down this way as far as we can go, but now we have one equation that has two things we don't know. We don't know velocity afterwards, and we don't know the thermal. This is going to be a problem. Is there any way we can get the velocity after? Not so much. Is there any way we can get the thermal after? Not so much. So we look back at the problem. And earlier we said that this problem was going to be a little bit of trouble because it doesn't say anything about friction. In this case, we're going to have to make the decision that friction is insignificant and just leave thermal energy out of it. So we leave thermal energy out of it. Now we have a problem we can solve because we have one equation with one unknown. So let's see what this looks like now. To solve for the velocity after, I'm going to circle what we're looking for. We're looking for this right here. First thing we have to do is get rid of the 8300, so we subtract 8300 from each side, and we get this step right here. We've got to get rid of the 1/2, so we multiply both sides by 2. 2 times 1/2 is 1. That gets rid of that. Now we have 33,220 equals 85 kilograms times V after squared. We've got to get rid of the 85 kilograms. We divide each side by 85 kilograms. And we get 390.8 joules per kilogram equals V after squared. We're still not done because the V after is squared, so we take the square root of each side. And we get 19.8 equals V after. And that's the solution to the problem. How would you practice this? Write down the word problem from above, attempt to solve it on your own without looking at the solution, check your answer. That concludes the problem. This has been Mr. Bixel's Tutorials. Thank you for watching.